Okay, in this section, we're going to look at a whole bunch of different vocabulary, but they have a lot of bearing on our unit here, very much so. Orientation, I think yeah, maybe I'll look at it first. We're going to look at the shape of a triangle and why it's so stable. We'll take into consideration some things like center of mass. We're going to look at different types of beams. We're not going to spend much time on that though. Columns, I think everybody knows what that is. Corrugation, not just cardboard, and lamination, not just paper. And then we'll end off with another piece of vocabulary here called performance requirements, which is fairly self-explanatory. Now, I want you to consider, or I want us to look at orientation. And I'm doing this all orally. I don't have a picture to show you. It's much better if you do it kind of in person. So yeah, we'll do the best we can here. So when you change the orientation or position of a structure, it can make it stronger. It can make it more stable as well. And the example that we use in the classroom is a meter stick. So if you take a meter stick and you have it nice and flat, you can bend it pretty easily, right? Because there's only a small amount of material that's supporting it. Now, we can make this meter stick way more stable and stronger just by changing its orientation. So if we turn it on its edge, now we have like 3 or 4 times the amount of material, that's the thickness of it, that's now supporting a load, right? So if you try to bend a meter stick sideways, you're going to have a really hard time because it's stronger that way. So when we change the position of certain materials or parts of structures, this can cause it to be much, much stronger. Okay, now triangles. Let's take a look at triangles. Now, just pause for a second here again and think of why a triangle is so stable. Okay, number one is they have a very wide base. And a wide base means wherever that center of mass is, center of gravity, wherever it is, if it's got a wide base, it has a much better chance of the center of mass being in between these 2 points somewhere, right? So the wider the base is, you increase the stability of that structure. Okay, now the other thing that's also very important here, makes a triangle sturdy, is its center of mass is low, right? Now we're not going to go right in the middle of this triangle and call that our center of mass, because that would mean that everything above this dot is the same amount of mass as everything below. And that is definitely not the case. Okay? If we were to split this evenly, the center of mass is probably down and around this area right here. Okay? The lower the center of mass is, the more stable a structure is. Okay? A term that you may have heard is if your center of mass is too high, then something can be top heavy. So here's a decorative vase. Here's my artistry. So let's say you have this really decorative vase, right? It has a very narrow base, right? And it's got a lot of mass on the top end. That makes it top heavy, and that makes it easier to tip over. Okay, so that's a very, unstable structure. So this one, our triangle, has a very low center of mass, therefore it's quite stable. Okay, types of beams. Let me just show you a couple. We're going to start with, oops. I'm going to start with I-beams. This is a typical I-beam right here. And it's fairly obvious why they call it an I-beam. You got one center piece of material, and just like your meter stick, actually, it's oriented vertically, right? And then you've got these horizontal parts to make it so it's nice. It's very easy to place these things together and to build things with. Very, very strong structure. Okay. L-beam, same idea, except, ooh, that's a good one right there. Except it's now the material is in the shape of an L, right? So you have one flat horizontal piece, and then your vertical piece is off to one side, and it looks like an L. These are really good brackets for where you have two materials coming together, one jutting out from the other one. These L-beams are really good for bracing corners and things like that. Definitely has its place. Box beams. Um, here's some, oh, there's a good box beam. So box beam, just as it implies, these are some picture of some good ones as well. You have material all the way around, and you have it's hollow in the middle. Okay? And box beams, any beam really, can be made out of any kind of material. Um, so that's what a box beam is. By far, the box beam uses up the most material, and probably the L beam typically uses the least amount of material. But if I were to take a guess, I would say that the I-beam would probably be the most stable and the strongest structure to build with. Something else we're going to look at, columns I'm not going to talk about. If you don't know what columns are, then look it up. Okay, corrugation though. Oftentimes we think about corrugated cardboard. So, so if you look at cardboard and you look at the edge, you'll see these little wavy pieces of paper in between there, right? So there's your wavy pieces of paper. Because we have this layer in there, um, that's what corrugation is, wavy pieces of material that help to strengthen a structure. Now, the reason why we use these waves, let's look at this one right here. It is in the shape, generally, of a triangle, right? So these are all triangles. They're rounded triangles, but they're still triangles. Right? And as such, they will add a significant amount of stability or strength, actually probably more strength, to these two pieces of paper that are put together. Okay, so that's corrugated cardboard. Not everything is, not all corrugations are cardboard though. If you take a look at, I'm just going to put in corrugated stuff. Okay, there's lots of things that are corrugated. Anything, I hope there's nothing inappropriate that pops up here. Okay, there's a chair. It's corrugated. That's weird. Okay, there's somebody's ceiling. These aren't really that great. There's a little decorative figure. Okay, these aren't that great. Let me find something else. There's lots of roofs that are corrugated. This is a pretty typical form of corrugation on a roof. This stuff here, you've probably seen that before. Whoops. This one on a farm is very, very common. You've probably, if you've been on a farm, you've probably seen this kind of stuff. Corrugated roofs like this can be made out of fiberglass. They can be made out of metal, different types of metal as well. The one that I really like to show people is, if you've ever been on a farm. Let's see. I don't know how to spell it actually. There we go. That was right. Okay, so a Quonset on a farm. Let's see. This is a good picture of one. So this Quonset right here, it's just a big chunk of corrugated metal. That's all it is, really. Okay, if you look at the sides of it, like there's these huge, very large waves, right? And when you get close to one of these, the metal is actually about 1/4 of an inch thick. So oftentimes farmers will have these Quonsets. They're very, very stable. It's a big open area in here. You got no beams, or columns supporting your materials up above, because this structure is so dang strong, right? So not only is it built out of corrugation, what shape are we looking at here? Basically a triangle, right? So that keeps cropping up. Okay, let's go back here. We got columns, we got corrugated. Lamination. Lamination is just combining layers of material together to create a stronger bond. And those materials that we stick together like that, they end up being quite strong, right? But it's combining layers of anything. So you paint a wall, now you've just strengthened that wall by adding another layer to it. Yes, laminating paper, it makes that paper stronger, right? More stable. You look at any kind of countertop material being placed on top, that's laminating. All of the desks in school, it's made out of particle board, the top layer, but then it's got this other lamination on top there. I actually don't know what the heck it is, but it's another layer added to the top of your desk. It's quite durable and adds to the strength of the desktop. So there's lots of things. Anytime you have layering of materials, you've got that's considered lamination. Okay, last thing, performance requirements. This is actually, if you just think about the term, performance, requirements. Performance is doing something. A requirement is what has to be done. So when structures are made or built, they have certain, before they're even put together actually, people determine what their performance requirements are. When they work, what are they going to have to be able to do? Okay? And they need to be able to do that, or else they're not a viable product. They're not a viable structure that we can use. Okay, so take a look at the definition. It says performance requirements are what loads a structure is required to handle. Basically, what are they supposed to do in order to be functional and safe for use? Okay. And so this kind of stuff, like I said, has to be determined before you even start putting it together. Okay, you have to think of what is it going to have to do. Okay, and I think that is the end of section 2. You bet.